In this video, I'm going to be going through my own work solutions for the AQA A-Level Physics Paper 1 from 2020. Now, it's important to have your own copy of your exam paper to hand, and the reason for this is that due to copyright restrictions, no printed material from AQA is shown in the video. So do make sure that you do have your own stuff to hand. Now, the 2020 series was actually disrupted quite a lot due to COVID. Now, the exam papers still say May or June on the front of them, but the series was actually sat in November 2020. In terms of the grade boundaries, the approximate mark out of 85 would be 66 and above for an A star, down to about 16 out of 85 for a grade E. I also have video work solutions for paper 2 and parts of paper 3 if you go over to A-Level Physics Online. But you can see here I've got a lot of props, and if you've already done the paper, you'll recognise the questions where these might come up. So let's start with question 1. So question number 1 is looking at some particle physics. Now what I'm going to do to solve this is just write down by the side Q, B and L. We're going to look at the conservation of charge, baryon number and lepton number. So in terms of charge, the 0 here represents that it has 0 charge. The electron has a charge of -1, whereas the muon, this is an anti-muon because it's got a plus up here, so that's got a charge of +1. And then this is a neutrino, so it has 0 charge. So we've got 0 charge on this side, and those make 0. So therefore charge is conserved. Looking possible. Baryon number, well, this isn't a baryon. A baryon is made out of 3 quarks, so that's got a baryon number of 0. This is a lepton, so it's got a baryon number of 0. That's a lepton, and so is this. So looking at the conservation of baryon number, it's all looking good. Now, in terms of lepton number, this isn't a lepton, so it's got a lepton number of 0. An electron has a lepton number of +1 because it's a lepton. This one over here is an anti-lepton, so it's actually got a lepton number of -1. All looking good so far. But then we have our anti-electron neutrino. Because it's an anti-electron neutrino, it's got a number of -1. So we can see here that the numbers on this side don't balance with this, and therefore the interaction isn't possible. I suppose, strictly speaking, we could say that the electron lepton number is conserved, but the muon lepton number isn't, if you wanted to kind of go into a little bit more depth. So for question number 1, I've shown that this is, I suppose, my way of working it out. And then what I'm going to do is just a quick statement underneath saying that lepton number is not conserved, and therefore this interaction is not possible. So it's always good just to state that very clearly in your answer. For the second question, we wanted to look at 2 possible quark configurations for a pion. Now, this is just some facts that you need to recall. I'm just going to get some Lego here. You know, if you've watched some of my other videos, I use a lot of Lego to represent different sorts of particles. And actually, when I've done this, I tend to use this yellow colour here to be my up quark. And when you have a pion, it can be made out of an up quark and an anti-up. So that's kind of this configuration, showing that one is upright and one is down. So one configuration could be up, anti-up. The other one, I've got these down quarks over here, just represented in red. And again, if you have a down and an anti-down, so that's the other configuration, down, anti-down, they're the 2 possible configurations of quarks. Okay, and again, this is just something that if you've done your revision, you'll be able to recall a quark configuration of certain particles. Now the next one is we're going to be looking at a kaon and an anti-kaon. Are these the same particle? Well, let's think about first of all the quark structure. Now the quark structure is either a down anti-strange or it's a strange anti-down. So again, let me just make that out of this. For this, I've just used an orange one to be my strange quark. So that's our kaon, that's our anti-kaon. And what we can see, even though they're made out of similar particles, they are not the same. The reason here is that the anti-kaon has a strange quark, and therefore it has a strangeness of -1 compared to the strangeness of 1 for a kaon. So because they don't have the strangeness, they are not the same particle. So this first page of questions, if you've done your revision and you can remember or recall the different quark combinations of different particles, that will really help you with this type of question. Okay, the second page, I suppose page number 3 really. This question is about a particle responsible for a force. Now, what I'm going to do is just put down k mu pi e minus, and then I'm going to have half a nucleon. Okay, and the reason for this is I'm just going to look at the mass, and I'm just going to find the mass of all of these particles just from the data book. And what I find is that the kaon has a mass of about 495, the muon 106, the pion 137, the electron 0.5, and the nucleon is in the order of 460. So I'm going to use this. I suppose this is my thought process about eliminating which of these particles, the kaon, the muon, or the pion, isn't the likely candidate for this question. So the particle would have a rest energy between that of an electron and half a nucleon. So whatever it is must be between these two values. And that means immediately the kaon, which is more massive, cannot be the right particle. So now it's really between these two. Both of them have a mass kind of somewhere between these two values. The next thing I'm going to consider is the force which is holding the nucleus together. Now, it is the strong nuclear force that holds the nucleus together. Now, the muon, which is actually this particle over here, is a lepton, and therefore it doesn't experience a strong nuclear force. So that means it can't be the muon, which is responsible for, I suppose, acting as that force carrier. And therefore, what we can then say is that the muon does not experience a strong force, and I suppose, and the kaon is too massive, and therefore the pion has the properties of the predicted particle. Okay, so that was all of question number 1. Now let's go on to question number 2. Question 2 starts with the separators, where we're looking at investigating stopping potential. This is kind of probably the most important part of that diagram. And the first question isn't really about this, but it's more about what is the photoelectric effect. Now, I suppose let's just zoom in on this part in here. What we'd have is maybe a surface of a metal, and there's going to be electrons within that. So I'm just going to tip out some electrons here with these bits of Lego representing electrons. We'd also have some incident photons. So it says monochromatic light, so that's just all of the same wavelength. And we can think about the wave-like or the kind of particle-like properties. So we've got these photons, and if that photon is above a certain energy, the electron will absorb the energy. It will move out of the material, and then any extra energy it has will be transferred to its kinetic energy. But there's going to be certain frequencies or certain energies of photons which can't be absorbed by the electron because that energy is just too low. It won't overcome the work function, and therefore we won't have any emission of these photoelectrons. Okay, so that is the photoelectric effect that we will have seen before. So the first question, part 1, we can basically state that the energy of a photon is proportional to its frequency. Or we could have said that E is equal to HF. So that's kind of the first statement, and we're talking here about the photons which are incident on that metal surface. And there is a minimum energy required to overcome the work function and remove a photoelectron. So this work function has the symbol phi. Effectively, once that electron has been removed from the surface of that metal, we then just refer to it as a photoelectron. So it's these two parts here that we need to get the 2 marks. For the second part, we have a graph, and the stopping potential down here is minus 1.25 volts. And if we look at the current up here in microamps, which is what we're measuring, so we tend to have a very small current which is actually in the circuit. It kind of crosses over here at about, I think about 26, up to the maximum value of 30 up here. So determine the number of photoelectrons per second leaving the photoemissive surface when the current is a maximum. So here the current I is a maximum, and that's going to be equal to 30 times 10 to the minus 6 amps. Don't forget, of course, we've got a microamp down there. I'm going to use the equation that says I is equal to Q over T. But we also know, I'm just going to do this in a different colour, that the total charge, Q, is going to be equal to the number of electrons times the elementary charge, the charge per electron. So we can therefore say that I is equal to NE divided by T. And this means that the number of electrons per second is equal to the current divided by the elementary charge. So here, the current, as we've set up here, is just 30 times 10 to the minus 6. The elementary charge, you can just look at it in your data sheet, but I'm sure by now you know it off by heart. That's just 1.60 times 10 to the minus 19. And this gives us a total number equal to 1.875. So to two significant figures, like I can read my data there, that's equal to 1.9 times 10 to the 14 per second. So the number of photoelectrons per second is 1.9 times 10 to the 14. For part 3, we need to explain why we get a constant value for the current when we have positive values of potential difference. So really that's why we have a constant value over here. Now the first thing we can say is that effectively we have an interaction between one photon that will release one photoelectron. And it does say above where the graph is on the other page that we have a source of constant intensity, and that means we're going to have the same number of photons landing on that surface per second. So we can say that the number of photoelectrons per second is proportional to the intensity of photons incident on the surface. So effectively we double the intensity, we'd have double the number of photons, therefore double the number of photoelectrons being emitted. Now that's going to be a constant value, and we have a constant current when all of the photoelectrons reach the anode. So what we mean by that, if I just bring this in, so again this is what we have, we're going to have the photons incident on the surface. All of these are going to be releasing a photoelectron which then has enough kinetic energy to actually reach the anode. And when every one of these that leaves this surface reaches this, there's going to be a point at which the current can't be any greater. So that's when we have this constant current when all of these leaving the surface reach the anode that we have over here. So that's part 3. For part 4, what we need to do really is explain why the current decreases as V becomes more negative. So this is explaining the shape of the graph that we have in figure 2. So why is that? Basically, when the photoelectrons are leaving that surface, they all have a range of kinetic energies. And when we have a negative potential difference, they're going to lose more kinetic energy as they're moving from the metal surface to the anode. So when there's a negative potential difference across this, even though they might be emitted with initially quite a high kinetic energy, they're going to lose some of that kinetic energy as they reach this part over here. And that means some of the photoelectrons might not actually make it all the way. So that's why we have a lower current. So when we have a negative potential difference, then we can say that the electrons lose kinetic energy as they cross to the anode, and as it becomes more negative, fewer of the photoelectrons have enough kinetic energy to actually, which is then I suppose transferred to their potential energy as they're crossing this gap, until none can make it. So effectively, when there's a really big potential difference across this, the electrons can't quite get across, and that's why we then have no electrons actually getting onto this part of the circuit and then going through the microammeter to actually record that current. Okay, next part is number 5. And this is looking at a different surface with a different work function. Now, effectively what we can say is that the stopping potential is proportional to the kinetic energy of these electrons. The greater the kinetic energy, the greater the stopping potential is going to be. Now we can also think about Einstein's photoelectric equation, where we can say that the energy of the photon is equal to the work function plus EK max. And again, sorry, this is the maximum kinetic energy. And what we can therefore say is that this maximum kinetic energy, EK, is equal to the energy of the photons minus the work function. And of course, this is also then going to be proportional to the stopping potential. Now, if we have the same source of coherent light, that means the energy of the photons is going to be the same. But if we have a lower value for the work function, this means that the value for the maximum kinetic energy of the photons is going to increase, and that means the stopping potential will also increase. So again, just putting that in a sentence. So with a lower work function for the same photon energy, the max kinetic energy increases, so the stopping potential also increases. So that's the end of question 2. Hopefully you've had the chance to experience this in real life, where you have 2 speakers set to the same signal generator, and then as you move around the classroom, potentially you might hear loud and quiet spots. Now the first question really is, what do we mean by a coherent wave? So it's not really actually anything to do with this diagram just yet. So what is coherence? So there's kind of 2 main parts to really talk about. So coherent waves have the same frequency and a constant phase difference. And in this particular example here, I suppose what we have is the 2 loudspeakers are connected to the same signal generator, so they must be receiving the same signal. And then it's just a case of just stating that here, that both speakers are connected to the same signal generator. So there we go, a mark for talking about coherent waves, and then the second mark is just referring back to the diagram and explaining why the signal from P and R, the signals there must be, P and Q must be coherent. Right, the next part, 3.2. This is really explaining why when the student moves from A, where it's a maximum, it's going to go quieter, probably the quietest point midway between the 2, then it gets louder, and then it's going to get quieter as they move on. So this is really due to how the 2 waves superpose, and especially, the interference of 2 different sources of waves. So what we can say is that at A and B, the 2 waves superpose, and that's a really important key word to get in there, and that's because they are perfectly in phase. So we have this constructive interference and a maximum is produced. We can then explain why it changes as you go from A to B. So I said that moving from A to B, there's going to be a path difference between the 2 waves because they'll have travelled a different distance, and as they become out of phase, their amplitude decreases to a minimum at a point midway between A and B. So if we imagine, you might hear a sound like this at A. As you go towards B, it decreases in volume, but it'll stay at the same pitch, and then as you move towards B, it's going to increase in volume once again. Part 3 starts with a load of information, and what I did was I just drew that onto my diagram that I had in the exam paper. So we've got the distance from O to A, we've got some distances from O to P, and also A to B, and so on. Now effectively what we can say is that the distance from P to B is going to be equal to 1 wavelength shorter than the distance from Q to B. So that means all we need to do is a bit of trigonometry to work out PB and QB. Now to do this, I'm just going to draw a couple of triangles just to help me out. Now these are not to scale, and you can see it's just a quick sketch diagram. So if this is P and this is B, then this distance down here is equal to 2.25 metres. Now the other thing is that if we sort of imagine a line across here, this distance here is going to be equal to 0.95 take away 0.15. And that's equal then to 0.80. And because this is the right angle triangle, we can say that PB is equal to the square root of 2.25 squared plus 0.80 squared. So there you go. Again, you can see it's just a quick sketch diagram, but it makes sense to me. So let's just work that out. So we've got 2.25 squared plus 0.8 squared. So that gives me an answer. I'm going to write it down as 2.38799. Okay, I think that's enough significant figures. We're going to do the same again, but now we're going to have the triangle, which is QB, and we're going to work out this side here. That's 2.25, and now from B down to Q is going to be equal to 0.95 plus 0.15, which is 1.10. So here, the line QB is equal to the square root 2.25 squared plus 1.1 squared, which equals 2.504449 5, I guess that's 0.50, isn't it? Okay, so plenty of stuff here. Now, this length, take away this length, should be equal to 1 wavelength. So QB, take away PB, is equal to the wavelength. In that case, this is just going to be equal to this number, take away 2.38799, which equals 0.1165. Again, it's always good to keep as many significant figures in your calculator, and that's approximately equal to 0.1 metre. So in this show me question, you were given this value, and I've given this value to more significant figures. Now the next question, pretty straightforward actually, we want to calculate the speed of sound. Now we know that V is equal to F lambda. We know that the frequency is 2,960, so that's 2960, and we're going to multiply that by the wavelength which we've just worked out. Now if you completely messed up this question, you could just use your value of 0.1. I'm going to multiply it by my value that I had worked out up here, which I've saved in the calculator, so just going to multiply that by 2960 to give a value of 344.9. So that's equal to two significant figures. I suppose we could go to, let's go to three significant figures. That's equal to 345. No, let's go to two significant figures because we were only given the distance as 0.95 and 0.15. So that's equal to 340 meters per second. And the other thing we can do here is just think, does that sound about right? Well, yeah, that's approximately the speed of sound in air. So we know we've done something which is correct. So I'm going to give that to two significant figures like the raw data given to us in the question. Now for the last part, again, we've got the same speakers at the same distance. We've got positions A, B and C, which has now been added onto the diagram. So what happens if the frequency of the sound is actually decreased? How's that going to affect the amplitude of the sound wave heard by the student? Okay, so louder, quieter, all that good stuff. Now what we can say is that from the wave speed equation, the wave speed is equal to V over the frequency. Now the wave speed is going to be constant because it's in the same air. So I'm just going to say that as the frequency decreases, the wavelength increases. So that would mean that B wouldn't necessarily be a point where we'd have a maximum sound. Now, if the student is at C, what's going to happen is that initially, if it was at the original frequency, C would be a point where it's not a maximum. However, as the frequency decreases, effectively, the point where we get the maximum is going to be moving this way. And so, at C, the sound would gradually increase in volume as the amplitude increased, and at C, the path difference increased to 1 wavelength. So that's why initially, as the frequency gradually went down, the wavelength would get longer and the volume or the amplitude at C would increase. And then beyond that, the sound would then become quieter as the frequency was increased further. So what you'd hear would sound something a little bit like this as that frequency decreased. So in question 4, we start with just a speed time graph, and on this I just converted my times on the bottom into seconds. So again, always check the units on the axis. This is between a couple of speed cameras you might get on the motorway to check the average speed. So my approach to this was just simply to break this up into some rectangles and triangles. And the maths is pretty straightforward, but it's just always worth really double checking all the values so you're using the right numbers in your calculator. And then what I'm going to do is like this one's just 15 times 90, you know the score. So I just wrote in all of the areas in these shapes. And that meant when it came to working out the average speed, it's just the total displacement over the time taken. This was equal to 4,815 divided by a time of 240 seconds, which gave my average speed as 20.06, which was a lot lower than the 22 metre per second speed limit. So did this vehicle actually speed? No, it didn't. And it's always worth writing that, just making it very clear that no, it wasn't speeding at this time. Now for the next part, we have the chevrons which go between cars. I actually built it out of Lego, of course. So effectively what you have is maybe a car in front of another car on the motorway. So here we've got a couple of different cars. And these are really a guide for the driver so that you're not getting too close to the vehicle in front, which is, can cause accidents. It's a lot more dangerous. So you should really all the time, but especially where there are chevrons, at least make sure that you can see the two chevrons between you when you're driving. So the question really said, suggest a value for D. So that's the distance between the vehicles where the speed limit is 31 meters per second. And it gave some data for the normal reaction time being between 1.6 and 2 seconds. Now I said that distance is going to be equal to VT. So that's D, the distance that we're trying to work out between these two things. Now that's going to be equal to the speed, which is 31 meters per second. And I took the upper estimate of time of 2 seconds. Now you could really take any value between those. I took that, and that gives me an answer equal to 62 meters. So that's an appropriate thing. And I suppose with human reaction time, because it varies between 1.6 and 2, I took the worst case scenario of 2 seconds. So there we go. That one there. Quite enjoyed building that. But now let's go on to the next question, which is part 3. Now for this, there is a load of information and there are several different approaches, but what we want to work out is the time and the distance. Now you could say that the kinetic energy stored by that vehicle, work is done on that by the brakes. And therefore you could say that a half mv squared is equal to that force times the distance. Now there are different approaches. This is the one that I took. Now I can then rearrange this to say that S, the distance it takes to stop, is equal to mv squared divided by 2 times the force. Now in the question, it gives you the mass of the car, how quickly it's going, and also the force applied. So that's why I went for this approach initially to find the total distance. So that's just equal to 1200 times 31 squared divided by 2 multiplied by 6,800 because the force was given in kilonewtons. And then when you do that on your calculator, we get a value equal to 84.79. Okay, so when it comes to working out my distance down here, I put that down as 85 meters, and that's to two significant figures like our data in the question for things like the speed or the velocity. Now to work out the time, I then went down the SUVAT approach. So I'm just going to write down SUVAT down here. We know the distance is 84.79. We know the final speed is 0, so that's distance in meters, meters per second. We know the initial velocity was 31 meters per second. We don't know the acceleration and we don't know the time, and that's what we're trying to find out. So which SUVAT equation doesn't have an A in it? We can basically say that S is equal to U plus V over 2 multiplied by T, and that means then T is equal to 2S over U plus V. So the time taken was 2 times 84.79 divided by 0 plus 31, and here that then gave a time equal to 5.47. So my time that I put down at the bottom here, I put down as 5.5 seconds. Now that was my approach. There are loads of different ways you could do it. I think the MARC scheme suggested you use force equals mass times acceleration. And if you know the force and the mass, we could work out the acceleration. We could then use that to fill in SUVAT to then find the values for S and T. But ultimately, because we're assuming that things are 100% efficient, it doesn't really matter which approach you take, you will still get to the correct answer. And it's important, super important, that any numbers that you calculate that you use in a subsequent calculation, like 84.79, you write down as many decimal places as possible, maybe store them in your calculator, and that means that you're not rounding down too early. So the next bit, we've got a suggestion. Why is it that the separation of chevrons from here to here, why does it not take into account the distance travelled by a car coming to rest after the brakes are applied? So really, these chevrons are to do with the thinking distance, which is the time it takes for somebody to react by the time they put the brakes on. Now imagine that this car had started braking, this car saw the car in front had started braking, there'd then be this thinking distance when it's the person is still reacting, and then, even if they put the brakes on here, the cars would then both be slowing down at the same rate, and now we kind of think about the braking distance. Now the braking distance, independent of thinking distance, that would be the same for all vehicles, and the idea being that by keeping these far apart, you don't have the collisions where this car is slowing down and this person is still thinking about what to do before they actually apply the brakes. So, in answer to this, we could basically say that assume the braking distance is the same, and the only difference is the reaction time of the driver behind. Okay. Another approach, you could have said that if you had the distance between these equal to the total stopping distance, actually that probably wouldn't be realistic, because a car travelling at 70 miles an hour on the motorway is going to take a long way to brake. And if you had these too far apart, then drivers would just ignore them because they just wouldn't be reasonable to actually allow traffic to flow. So yeah, basically, this is really about the thinking distance, and then that means it allows the vehicles not to collide. And then once they put the brakes on, they all slow down in approximately the same distance. Hopefully that makes sense. Right, now we're going to go on to this car moving around a circular bit of track. And there's a picture or diagram in figure 7. And then figure 8 has this thing here showing this vehicle on that banked corner, how the weight is acting vertically down, but now the normal reaction force is at 90 degrees to the slope. Now, the numbers on this, we know that that's equal to 5 degrees, and that means this angle here is also equal to 5 degrees as well. Okay, that's going to be important. So the question wants us to work out an appropriate speed of that vehicle. Now, let's think about the forces. We can think about the forces vertically and horizontally. Now, in the horizontal direction, we can say there's going to be a horizontal component of that reaction force, which is acting in towards the centre of that circle, and that is going to be equal to n times sine of 5 degrees. Okay, and that's going to be equal, or that's going to be providing the centripetal force, which is equal to mv squared over r. So that depends on the mass of the vehicle, how quickly it's going, and the radius of that turn. If we think about the forces in the vertical direction, well, the car, it's not going to be moving up or down, it's going to be staying at the same height, and therefore the vertical component of that normal contact force, n, is going to be multiplied by cos 5.0. So we're looking at the vertical component of this force here, and that's going to be equal to the weight of that vehicle acting down, which is equal to mg. Now we can rearrange this to say that n is equal to mg divided by cos theta, or in this case cos 5 degrees, and we can then substitute it back into this equation up here to say that mg multiplied by sine of 5 degrees divided by cos of 5 degrees, which is what we had over here, that's equal now to mv squared over r. Now, sine over cos is equal to tan, and we can also see that the m's cancel. So what we can say is that g tan 5 degrees is equal to v squared over r, and we're trying to find out this value for v. So v is going to be equal to the square root of g r tan of 5. Okay, now really I suppose I probably should have called that theta, would have made this a lot neater, but you get the idea. Basically, if we know the gravitational field strength, the radius of the turn, and then do tan of 5 degrees, that will tell us the speed. And if I just put those numbers into my calculator, this gives me a number equal to 13.1, which is equal to 13 meters per second, to two significant figures like the angle that we were given. So this one over here, looking at circular motion, looking at resolving forces in both horizontal and vertical directions to give a value of about 13 meters per second. That's the end of question 4. Now on to question 5. So in this question we have 3 12-volt bulbs here, which are going to be in parallel. We have our variable power supply. That one's actually made out of Lego, so maybe not as useful. But I do have my real, actual proper power supply here. When I turn it on, oh, bit of jiggling here. There we go. So that is working. We've got our 3 lamps in parallel. And initially, they're connected with a small amount of copper wire. So this is highly conductive, it's quite thick, it's quite short, and therefore negligible resistance. And the first thing we want to do is show that the resistance of one of the lamps, when it's at 12 volts, is about 100 ohms. So let me just put this up here. It's kind of in the way, isn't it? Okay, so there we go. So one of the equations for working out electrical power is equal to V squared over R. And that means the resistance is equal to V squared over P. Now, it says that they are 12-volt bulbs, so that's 12 squared, divided by the power rating, which in the question is given to us as 1.5. And so that is going to be 144 divided by 1.5, which is equal to 96. And 96 is approximately equal to 100. So that's going to be the resistance of each of these lamps. So that's equal to 100 ohms. Well, the next part, so initially it says the power supply is connected with this piece of copper, and we want to calculate the current in the power supply. Well, we can do that by looking at the current here, here, and here, adding them together, and that's going to be the current drawn from the supply. Now we know, of course, that P is equal to VI, and therefore that current is equal to the power of one of these divided by the potential difference, which is just equal to 1.5 divided by 12, which equals 0.125 amps. For each of those, we're going to multiply that by 3, and 3 times 0.125 is just equal to 0.375, not even needing a calculator for that. So I'm going to give my final current as 0.38 of an amp. And again, that's to two significant figures like the raw data that we have down here. For part 3, it says that the copper is replaced with some constantin wire. This one over here, from the Scientific Wire Company, no less. It's going to be 2.8 meters long, and there's going to be 2 different 2.8 meter bits of wire. But we want to just calculate the resistance of each length. Now, we're going to use the equation that says resistance R is equal to rho L over A. Now, as often the case, we don't know the area directly, but we do know that the area of that piece of wire is equal to pi d squared over 4. And if we put this into there, we can then say that the resistance is equal to 4 rho L divided by pi d squared. And then we're just going to take the data from in the question. So that's just equal to 4 multiplied by the resistivity, which is 4.9 times 10 to the minus 7, multiplying that by 2.8, dividing by pi times the diameter of the wire is 0.19 times 10 to the minus 3 all squared. Okay, so lots of numbers here. Pretty straightforward though. If you do it on your calculator, we get the resistance equal to 48.39, which is about 50 ohms. So again, this is the number that we're trying to get towards, and I've given my answer to a couple more significant figures to show I've actually calculated it. So we know the resistance of each of these 3 things. We know the resistance of each bit of wire. What we can now show, or actually what we can actually discuss, is that when we've got this in the circuit, when we turn it back on again, even though it's set to the same potential difference, the lamps actually appear a lot dimmer than they were before that. So does the demonstration actually achieve that? Now, the first thing I did for this question here was I looked at the total resistance of that circuit. Now, that's going to be equal to the resistance of each bit of constantin wire, which we worked out up here. So I'm just going to use my value there of 48.39 multiplied by 2. But we then have 3 lamps which are in parallel, and that means when they're in parallel, if we know the resistance of this lamp, the combined resistance is going to be a third of that. And we worked that out as 96 ohms for each lamp, so that's going to be 96 divided by 3. So that means our total resistance is equal to, by my calculations, about 128.78. Now, more significant figures than we need, but we can then use this if we've got a power supply which is set to 12 volts. We can say that the current drawn by the power supply is equal to V over R, which is just 12 over this value here, so 128.78. And that's about 0.093 amps. Now before, as we worked out in one of the previous questions, when these were initially on and quite bright, they were drawing a total of about 0.375 amps. So when you have the constantan wire in the circuit, there's a much greater resistance, and that means the current is going to be less. And so this current, which is being drawn from the power supply, is then going to be split 3 ways. So we can basically say that the current through each lamp will be a lot lower, so they will be dimmer than before. And actually sometimes you might notice that even if there's current drawn, it might appear that the lamps are actually off. So that was my answer to part 4. Now question 5 is kind of related to this, but actually we don't need any of this knowledge because question 5 is really about superconductivity. So what are the pros and cons of using superconductors over long distances? Well, I suppose one of the big advantages is if you've got a superconductor, the resistance is equal to 0. It's not a low value of resistance, it is equal to 0, and therefore there are no power losses. But I suppose the reason we're not using them at the moment is, I suppose, that in order for something to be a superconductor, it has to be below its critical temperature. And this temperature is actually very hard to reach in practice, and especially over a big distance. So I'm just going to say that the temperature has to be very low, below the critical temperature of that superconductor. And this is often, maybe something like minus 200. And that's very difficult to achieve over long distances if you think about what this would actually entail in the real world. So that was the end of section A. We're now going to move on to some multiple choice questions where I'm going to explain all of the answers to you. Okay, multiple choice questions. The first one is about mechanical power. Well, it's not a vector quantity, it's a scalar because it's a power. It's not measured in joules, so that would be energy. The next one, could it be this? Well, we know that energy could be calculated with maybe half mv squared, and we're going to divide that by time. Now the base units for mass are kilograms, base units for velocity are meters per second. We've got meters per second squared, so that's m squared second to the minus 2, and we're going to divide that by seconds, which is the base unit for time. So that would then become kilogram meter squared second to the minus 3. So here, C is the correct answer. And it isn't D because power isn't force times distance. Power is equal to force multiplied by velocity. So that's why it's not D. For number 7, we've got water waves, they've got a wave speed, and there's an equation that we've never seen before. But what we can say is because V is equal to the square root of k lambda, we can say that V squared is equal to k lambda, and that means k has the units of V squared over lambda. Now the units for that, it's going to be meters per second squared, so that's going to be equal to meters squared second to the minus 2, divided that by meters, which is then meters second to the minus 2. So just a bit of base unit stuff. So I've worked this out before I've even looked at my answers, and I can see that this ties up with question or answer A. So that's number 7. So for question 8, I've got the equation for kinetic energy, which is a half mv squared, and that's going to be equal to the energy of that photon, which has been given to us in electron volts. Now to work out the velocity, I'm just going to rearrange this to say 2 times the kinetic energy over the mass square rooted is V, and that's going to be equal to 2 times the photon energy, which is 1 times 10 to the 18 electron volts. I'm going to multiply that then by our conversion factor to go from electron volts to joules, which is 1.6 times 10 to the minus 19. Divide that by the mass of 0.03, and we're going to square root that. And when we do that, we find that this is equal to 3.266 meters per second, and the closest one of these to 3.26 is just 3. So the answer for 8 is B. For this one, we've got this reaction over here. We want to know what this particle is. Now, whatever the numbers on the bottom on the left are going to be the same as the numbers at the bottom on the right. So we've got 1 and 1, and we've got 2. So that must have a number of 0. And the numbers at the top must all add up. So we've got 2 and 3, and we've got 4 and 1. So we've got something which has no protons and 1 nucleon, and therefore this must be a neutron. Okay, even if you've never seen this before, although this often comes up where we have the fusion of deuterium and tritium to make helium and some neutrons, you don't need to know that. You just need to look at the conservation of proton and mass numbers, and therefore the answer for this is B, a neutron. For number 10, we've got something which initially has 232 nucleons and 90 protons. Now it says it decays by 1 alpha emission. So when you've had an alpha emission, the number on the bottom is going to go down by 2, down to 88, and the number at the top goes down by 4, down to 228. So this is after an alpha emission. We then have a beta emission, and when you have beta emission, if it's beta minus, this is when a neutron changes into a proton and emits this high-speed electron, and that means the number on the bottom goes up by 1 to 89, but the total number of nucleons stays the same at 228. And then we're going to have another beta minus emitted, so that goes up again to 90, and the number at the top stays as 228. So whatever it is, it must have 228 nucleons and 90, and therefore the answer is C, this particular isotope of thorium. What do we measure in kilowatt hours? Well, kilowatts is used to measure power, hours is used to record time, and power times time is equal to energy. So a kilowatt hour is just another unit of energy, and therefore the answer is C. So for number 12, we have various statements. It's worth reading them all before you make your answer. So an electron collides with an isolated atom, and it raises up an electron to a higher energy level. So is the colliding electron captured by the nucleus? That's not correct. Is a photon emitted as the electron goes up to a higher level? Well, no, the photon would be emitted as it drops back down, so it can't be B. And for C, an electron is emitted when the excited electron returns to the ground state. Now again, this is a photon is emitted as the electron drops back down energy levels, and so by default the answer must be D. Which is actually true, that the colliding electron transfers energy to the atomic electron. So some of the energy of the incoming electron is transferred to the one which is in the atom, and that's why it rises up. So here, the answer for 12 is D. For 13, we've got the shapes of these graphs. Now, we want to look at the relationship between momentum and wavelength. Now, you might recall that lambda equals h over mv, or h over p. So this is the de Broglie wavelength, is related to the momentum by Planck's constant, and therefore the wavelength is proportional or inversely proportional to the momentum. So which graph shows something which is inversely proportional? Well, this shows that these two things, we've got momentum and wavelength would be proportional, so it can't be this one. And actually it's this one over here. As this number gets bigger, this one gets lower. Now this one looks similar, but here we actually have something meeting the axis, and that would mean effectively at some point we'd have 1 over 0, which would be infinite, so it can't be this one. It's not that one. And here, this just shows how as one value increases, the other one decreases. So the answer for 13 is A. So light is travelling from glass to air, and as it does so, it's going to speed up. We've got the wavelength, we've got the speed, and also the photon energy E. So what happens to the speed? Well, it actually increases as it goes to this optically less dense medium, so it can't be B or C. In actual fact, if you look at A and D, the wavelength increases for both of them, so that doesn't really give us any clues. So that's true, and that's true. Now the other thing is that the frequency of that light is going to stay the same, and we know that because E is equal to HF, the photon energy is proportional to frequency. Now the frequency stays the same, it's just the wavelength and speed that change, and therefore the photon energy does not change is a correct statement, and that's why the answer for 14 is D. For 15, we've got a graph where we've got displacement, sometimes given a symbol x, when it looks at waves and kind of simple harmonic motion and things. And we've got the distance along here. Now that's important. The amplitude is the distance from the rest position to the maximum displacement. So here W is equal to the amplitude. So A and D are correct and it can't be B or C. Now Z is the wavelength, because on this axis we have distance. If we had time on this axis, that would be the period, but because we've got a distance measured on the axis, this must be a length, and therefore Z is a wavelength. So the answer for 15 is A. And there's another graph looking, which I've kind of just drawn in over here, which statement is correct. So the phase difference between particles P and S is lambda over 2, potentially. The distance between P and R is 6. How do we know that? Well, we do know that because V is equal to F lambda, the wavelength is equal to the speed over the frequency, which is given to us as 24 and 4. So the wavelength is actually 6.0 centimetres. So P to R is actually 3 centimetres, so it's not that. The velocity of particle Q is a maximum? Well, no, because at this point it's got to its maximum displacement from its rest position. So at that point, actually, its velocity, is actually 0. It would have its maximum velocities at P and R. So again, linking that to some work you might have done about simple harmonic motion and pendulums, for example. P and R are in phase. Well, actually, they're half a wavelength apart, and actually that means they're out of phase by 180 degrees or by pi radians. So that's not true. In actual fact, if we think about from P all the way to the end of that wave cycle, that's effectively equal to 2 pi radians. So from P to R is equal to pi radians, and that means like the distance from S to this point here is out by a factor of pi over 2. So actually here, 16A is the correct answer. So the phase difference between this position here and this position here is equal to pi over 2 radians. 17 has a diagram of 2 polaroid filters. When they are lined up, we get the maximum intensity of light going through. When the one behind is rotated by a quarter of a turn, that's equal to pi over 2 radians, and we get a minimum value of light being actually going through, because it kind of blocks out all the light. As we go through another quarter rotation, we now have all of that light going through again once the 2 filters are lined up. So basically, every time I rotate it by pi radians, we get another maxima. So effectively here, the answer is going to be C, because we have the maximum intensity every time it rotates through 180 degrees, which is pi radians. So that's why it's pi, 2 pi, and 3 pi. Number 18, I think it's always useful to draw a little diagram. So we've got stationary waves set up on a rope of length 1 metre fixed at both ends. So effectively this is our rope. We've got fixed ends here and here. And what we're going to have is a node at each end. And then we're going to set up the first bit. So the first harmonic has a wavelength of 2 meters. So the first harmonic looks like this. Okay, and here the length of that string is equal to 1.0 meters. Okay, now the first harmonic is where this length is going to be equal to lambda over 2, which in this case is 2.0 over 2, which equals 1.0 meters. So the first statement is correct, but we want to know what isn't correct in this question. The midpoint of the rope is always stationary for even numbered harmonics. So that's an odd harmonic. The next one, which is even, is going to be something like this. Okay, so we've got a node in the middle. So that's the first, that's the second. The third one I'm not going to draw it, but the fourth one, we just have something that kind of looks like that and that again. So this is my rough diagram, and you can see that every time we have an even number, we have a node in the middle, so this statement is also true. A harmonic of wavelength 4 meters, of wavelength 0.4 can be set up on the rope. So here we've got a wavelength. Well, if that's 1 meter, that's 50 centimeters. So that's a wavelength of 0.5. Can we have a wavelength of 0.4? Well, I reckon actually we can. So I'm going to just put a node here and here, and then we'd have one here, here, 1, 2, 3, here. Okay, so let's see. So we'd have something that looks like is that right? So yeah, so that's 1 meter. So from here to here, the distance between these things here is equal to 0.4 of a meter. So yeah, you can have, like the fifth harmonic has a wavelength of 0.4, so that's correct. And that means the one that isn't correct must be D. We'll just confirm that. There are 5 nodes on the rope for the fifth harmonic. So the fifth harmonic, we've got 1, 2, 3, 4, 5, 6. So that statement is incorrect, and that's why D is the right answer. Okay, and again, draw a diagram. It's just for you to kind of work it through, to kind of visualize what's said in the question. For 19, again, I think a diagram is actually really useful, and this really helped me out with this one. So we've basically got like our diffraction grating here. We've got like the first order. We then have our second, here's our first 0th order, first order, and then we'd have our second order. Now it says in the question that the angle between the second order diffraction maxima is 44 degrees. So between this and this is equal to 44 degrees. So this angle here is equal to 22 degrees when n is equal to 2. I'm then going to use the equation that says d sine theta is equal to n lambda, and we want to work out lambda. So lambda is going to be equal to d, and the distance between the diffraction gratings is equal to 1 over 450, and that's 450 times 10 to the 5. We're going to multiply that by sine of 22 degrees. We're going to divide that by n, which is 2. And when I did that, I found that the wavelength was equal to 4.162 times 10 to the minus 7, which is 416 times 10 to the minus 9. So here, that's why my answer was B. So before I even looked at the answers, I worked this out. I suspect a lot of people might have gone wrong by not actually drawing the diagram and actually looking at the angle appropriately. For this one, about moments, I basically said that this way is going to be my clockwise or kind of positive moment, and I just worked them all out. So the total clockwise moment is going to be equal to this one here, which is 6 times 0.2, plus this one here, which is 10 times 0.5, plus 4 times 0.7, and then take away 20 times 0.5. Okay, so that's my anti-clockwise moment if we take moments about this point over here. So when we add this up, that's just equal to 1.2 plus 5 plus 2.8 take away 10, which is equal to minus 1. So at the moment, the system is not in equilibrium, so that's not correct. Also, if we added another 10 Newton force down here, we then have 20 newtons up and 30 newtons down. So that means that we'd have unbalanced forces, so the system would not be in equilibrium again. Okay, so to make it in equilibrium, do we need to provide a clockwise or anti-clockwise moment? Well, at the moment we have an anti-clockwise moment, so we need to provide a clockwise moment of 1 Newton meter. So here, the answer is C. This one I actually found surprisingly tricky initially. What I did though was, I suppose a bit of a logic problem, a kind of bit of Suvat. I wrote down Suvat, as always, if we've got motions of projectiles. We know the distance it falls through is 0.80 meters. We know initially it starts at 0. We don't know its final velocity, but we know the acceleration is 9.81 meters per second squared. And what I did was I looked at working out the time it takes to fall. Okay, and so to work out the time, we can say that S is equal to ut plus half at squared. U is 0, and therefore the time is going to be equal to 2s over a square rooted. And when I did that, I put in 2 times 0.80, divided it by 9.81, and it meant the time it took to fall for one droplet was 0.404 seconds. Now what that means is the first droplet to fall is going to hit the ground after 0.404 seconds, and there's going to be another droplet in the air that was released 0.20 seconds behind it. So that time that the other droplet has been falling for is going to be equal to 0.404 take away 0.20, which equals 0.204 seconds. Okay, so the first droplet took 0.404 seconds to hit the floor, and that means the other droplet, I'm just going to change to red, had been falling for 0.204 seconds. So I can then write down SUVAT yet again. I'm just going to do it in here. Again, this is my working out. It's a bit messy. I understand it. Hopefully you do as well. But you can always look at working in the back of the exam booklet if you need more space. We don't know how far it's fallen. U is 0, acceleration is 9.81, and the time is 0.204. And we want to know the distance. And again, we can use this equation here, that S equals ut plus a half at squared. So S is equal to, because U is 0, a half at squared, which is a half times 9.81 times 0.204 squared. And that then gives me an answer equal to 0.20. So basically, the answer for this, looking at the numbers here, is B. And we can see that basically the first droplet takes about 0.4 of a second to fall 0.8 of a metre, but the second droplet takes half the time to fall quarter of the distance. And that's the kind of proof of that using some SUVAT. Quite a lot for 1 mark. The next one, we've got some momentum before and after. So we know that P before is equal to the momentum afterwards. And I said the pellet had a velocity of U1 of 200, mass 1 of 5 grams. And so we can say that M1U1, that's the mass and speed of the pellet beforehand, is equal to the combined mass times its combined velocity after that collision, provided it's a closed system and so on. That means the final velocity is going to be equal to M1 times U1, which is just 5.0 times 200 divided by 100. And that's because the 5 is added to the 95, and I've kept them both in grams because we're dividing one by the other, equal to 10 meters per second. And then the next thing I'm going to look at is if we know how quickly it initially went up in the air, we can say that all of that initial kinetic energy, EK, ended up as a gravitational potential energy of that particle. So we can say that half mv squared is equal to mgh. The masses cancel, and we want to find out h. So h is equal to v squared over 2g. Now you can of course use SUVAT, you get a very similar equation, and that's going to be equal to 10 squared divided by 2.981. So that's effectively 100 divided by 20. And 100 divided by 20 is just over 5, but again, you can always check it in your calculator as 5.0968, and that means here A is the correct answer. It goes about 5.1 meters up into the air. Right, 23, efficiency of a motor. We know that the power out is going to be equal to the energy divided by time, which is equal to mgh divided by t, because this is the useful energy transfer. It's increasing gravitational potential energy, and mg is equal to its weight, so that's equal to wh over t. Now the power in is going to be equal to the electrical power in, which equals vi, and the efficiency is going to be equal to the power out divided by the power in, which equals wh over t divided by vi. And here, wh over vit is just equal to a. So again, I just worked this out before I actually looked at the answers. So there we go, that was 23. So 24 has some equations that we maybe haven't seen before, but I'm going to say that Vmax is equal to omega A. And we know, of course, that omega is equal to 2 pi f. So that's 2 pi f A. Now, if we want to look at the kinetic energy, we're going to look at Vmax squared. So that's going to be, and if I just do Vmax squared, that's going to be all of this squared. So that's 4 pi squared f squared A. Okay, and of course, kinetic energy is just a half mv squared. So the kinetic energy is equal to a half of this, so that's 2 times the mass times pi squared f squared A. Okay, so quite a lot over here. And then looking at the different options here, so we've got 2 pi squared f squared A. Oh yeah, sorry, that should be a squared, and that should be a squared as well. So therefore, it's a long paper, isn't it? 24. I mean, by the time you're working through this, you're going to be tired, aren't you? So 24, the answer I came up with was B. Okay, 25. This is to do with something to do with simple harmonic motion. Now we know that T is equal to 2 pi root m over k. And the first thing I did was I took the numbers from in the question. So we've got a mass of 0.90 kilogram. The spring constant was 80. And when I did that, I found that my time period for one oscillation was 0.666 seconds. Frequency, 1 over time period. So 1 over 2/3 is 3 over 2. And therefore that's equal to 1.50 hertz. So here, looking at the answers here now, the correct answer was C. For 26, we've got some data. We've got the extension, or delta L, and also the weight. And that weight is going to be providing the force that's causing it to change. Now, the Young modulus is equal to the stress over the strain. Now, you don't always use these symbols with AQA, but effectively the stress is equal to the force over area divided by the strain, which is the extension, over the original length. And if we rearrange all of this, we can say that the Young modulus E is equal to FL over delta LA. Now, here, the gradient is going to be equal to delta L divided by F. And if we bring the delta L up here, we bring the F down, that means that's equal to the length divided by EA. So this is equal to our gradient, and that's equal to L divided by EA, and the correct option down here is D. So the equation for the Young modulus, stress over strain, rearranged, and then relating that to the graph and what it actually shows. 27. This one is effectively a circuit where what we can say is that the ratio of P to Q and their resistances is going to be the same as the ratio of R to T. And the reason for that is that when the resistance of this to this is the same as the ratio of this to this, there's going to be zero potential difference between these two things. Okay, and therefore the voltmeter reading is going to be equal to 0. Now, when the temperature of the thermistor increases, you've got to remember this kind of graph here, as the temperature goes up, the resistance goes down. So the resistance of this is going to be going down. Now, to make sure that these have the same ratio, this means the resistance of resistor R must also happen at the same time. So we reduce that resistance, we need to reduce this resistance so that R to T is the same as P to Q, and therefore here D is the correct answer. Does that make sense? Hopefully. Right, 28. Oh, this one I found quite tricky. Now, how can we do it? Basically, what is the current in the resistor? Well, the current in the resistor I is going to be equal to the potential difference across it divided by the total resistance of that circuit, which I'm going to call RT. Now, each of these has an EMF. That's going to be E, E, and E. And they also have a small internal resistance R. Now, around any closed loop in the circuit, the sum of the EMFs is going to be equal to the same as the potential differences. and therefore the value for the potential difference across this is going to be the same as one of those EMFs. Okay, so if we had a voltmeter across this, the reading on it would be equal to E, because here if we look at this loop or this loop or this loop, this EMF is equal to this potential difference. Now, what is the total resistance of that circuit? Well, the total resistance RT is going to be equal to the resistance of this R plus the combined resistance of these three cells in parallel. Now, effectively, because we've got R, R, and R, their combined resistance is going to be equal to a third of that, which is equal to R over 3. So here, that's equal to E over the total resistance, which is R plus R over 3. Now, that looks a bit messy, so what we're going to do is multiply the top and the bottom by 3 to say 3E over 3R, and R over 3 times by 3 is just R. So here the answer for 28 is actually A. But that one there I thought was quite tricky. We don't often have many questions where you've got cells, especially where we need to consider their internal resistance in parallel. For question 29, we have the reading across the cell, which initially is V. And effectively, we could put the voltmeter here, or we could put it across here. So I'm just going to imagine we've got our voltmeter across our resistor that's got a resistance of 2.0 ohms, and it gives a reading of V. Now, as soon as we close the switch, we then have to consider the total resistance, including the internal resistance. And now the reading on the voltmeter goes down to a third of what it was. And effectively, that means if we were to maybe think about what's going across here, we'd have the same EMF of the cell, but now effectively you've got 2V over 3, which is the drop over here. Okay, does that kind of make sense? So effectively, we had V over 2 ohms. Now that's gone to a third of its original value because the total resistance of the whole circuit must be equal to 6 ohms. So that means the internal resistance, little r, is equal to 4 ohms. Okay, that's kind of my way of sort of working through it. So here, the answer for 29 I put down as C. And then number 30, we've got the period of a simple pendulum is doubled when the pendulum length is increased by 1.8. So I'm going to use the equation that says the time period is equal to 2 pi root L over G. And if we've got the same gravitational field strength and pi is a constant, we can say that the time period is proportional to root L. And that means the time period over root L is going to be a constant value. Now, after we increase the length, the time period doubles to 2t, and here the length was whatever it was, L, plus 1.8 meters. So that's my approach. I then squared the top and the bottom of these, so we've got t squared over L is equal to 4t squared over L plus 1.8. Okay, so I just squared this and all of this. We can then think, well, okay, let's maybe simplify this as much as possible. We've got t's on the left and the right. And therefore I said that 1 over L is equal to 4 over L plus 1.8. Or we could also say that L plus 1.8 is equal to 4L. So 1.8 is equal to 3L, divide both by sides by 3 to say L is equal to 0.6, which is actually one of the answers here, luckily, which is B. So here, that was my approach, just using the equation for a pendulum, and we looked at the ratio, because everything else is a constant, that t over root L is going to be equal to 2t over L plus 1.8. And therefore, the length for the pendulum was 0.6 of a metre. And that was the last question on paper 1. So overall, I thought some really nice questions. They're pretty fair. Some of them were pretty tricky, as every paper is going to have things to really kind of differentiate at that very high end. And again, here are the grade boundaries where you can see how your combined mark over papers 1, 2, 3A and 3B gives you this mark out of 250. And again, if you'd like to look at papers 2 and parts of paper 3, head on to the other parts of my website where you can find my full work solutions to these as well. So thank you so much for watching. I know it's been a big thing, but hopefully this has been helpful to you. Thank you so much.